Thank you all for being connected. I guess this webinar will be recorded and then it will be shared on the usual social media in case you want to watch it again, or for those who cannot make it today. So on my side, my name is Sebastian Fay. I'm coordinating this project, SIGG Twin, and I'm pleased to be there with quite a few other partners. Thank you for joining. I will just now make a try to share my screen. It should work in a few seconds, hopefully. Voila. Are you able to see my screen? No. I guess the moderator. Okay, this works.
Yeah, you are.
That's also quite a new system for us, and we are, all from research organizations and companies that are innovating every day. So I guess that's the first way to innovate, to try to use this new broadcast system. Anyway, so thank you all again for being here today. This is the fourth edition of a webinar for this European project 6G Twin, which is about integrating network digital twinning into future AI-based 6G systems. Once again, my name is Sebastian Fay. I come from the Luxembourg Institute of Science and Technology, and I will now just briefly introduce the concept of the project and then give the floor to the many other partners who have joined today for this webinar. So first of all, just to give you a bit overview of the main objective of the project. So we are dealing here with a concept which is well known among the 5G, 6G and network community, which is called network digital twinning. This is, a concept that has been seen in quite a few papers and, that has been around for a few years, let's say. But now with this project, the idea is to try to make it slightly more concrete. So our objective is really to design, to implement, and to validate, new systems targeting future 6G systems that incorporates this network digital twinning as a core mechanism for, let's say, planning and control of future scenarios, at least the scenarios that are foreseen by the European community and, the community working on 6G networks, let's say. This initiative is funded by the Smart Network and Services Joint Undertaking, SNSGU. The project started more than 2 years ago, and it will end at the end of the year, meaning that we have quite concrete results to show you today. And so here at the bottom right, you can see an overview of the partners in the project. So this is quite a good balance between universities, research centers, and as well companies, of course, to bring all this to the reality and make the work a bit more applied and concrete, let's say. So in total, the project will deliver quite a few outcomes. So I will not start detailing them. I guess this is in the next presentations. But this is really ranging from models to prototypes. And I guess one of these prototypes and framework will be showcased today. We will have two main demonstrators in the project, which are currently being finalized. The first one is about teleoperated driving, and the second one is about energy efficiency. These are two key focus areas of the project. These are quite important as well for the 6G community, and that's the focus here on the project. So the idea of the first demonstrator, and again, I will not go into too many details because that's really at the core of the next presentations, but the first demonstrator is really related to this mobility domain. And we know that mobility is quite a big issue in Europe. I mean, on my side, I come from Luxembourg, so you can imagine Luxembourg is a huge cross-border area. We have quite a lot of traffic jams every day. So of course, we are seeing connectivity as a key solution, to enabling more automation and new mobility solutions. So here the idea is really to try to use, let's say, a digital twin to anticipate what could happen on the road. So using it as a network planning, let's say, solution to to help us and help the operators, with these kind of issues, that might happen on the road when you have teleoperated vehicles, typically. Here, these are just a few videos and screen caps of a few of the activities we have here in Belval, which is one of the campus we have in Luxembourg. So again, a cross-border area where we are running some of the experiments in the project. A second demonstrator is about energy savings. We know that it's now becoming a massive issue, not only for the telecommunications sector, but in general, for Europe and worldwide. We need to optimize the way we consume energy. This is a fact. And if we foresee what could happen with with telecommunications and networks, we know that in the future we will have more and more AI data. Many things will be distributed, so meaning that we need to anticipate a bit the way the energy is spent, let's say, on the network. So here the idea is to use network digital twinning to let's say, as a solution to react, to control in real time the network, and to achieve more energy efficiency. But again, I guess more details would be available later. That's the timeline of the project. So as I told you, we are towards the end of the project. One major milestone that has been achieved recently is the release of a federated simulation framework and some models. This is fully available to the community. This will be presented today, first time. So that's one of the major presentation we have for this fourth webinar. Then just a few words about the Zenodo community we have on the project. I guess it's a nice community webpage that you can join. So just go to Zenodo and then look at 6G Twin. You will see there all the publications we might have, scientific publications we might have at the moment. We obviously also have a website where you can find deliverables and more outcomes. But I really encourage you, if you are interested by the topic, to go there and probably to consult one of the latest paper we have published, which is a major work summarizing even detailing, because we have something like more than 30 pages, I guess, detailing the reference functional architecture we are using in the project. So I'm really encouraging you to go there. And on this word, you can find a QR code so that you can go to 6gtwin.eu. But most importantly, you have the lineup of people who will present some of our recent activities today. So again, today the idea is really to focus this webinar on concrete outcomes we have generated so far. So to showcase what we have done when it comes to creating functional models, that are, let's say, that are making this network digital twin concept, which we are developing in the project. And then you will also have some concrete presentations of the co-simulation framework we have built and that is now available to the community. So thank you again for being here. And now I guess the floor is to Iskander, if I'm not mistaken, for the next part of the presentation. Thank you.
Iskander and myself who can share the presentation. Maybe I ask Iskander if you can. Thanks, Sebastian. He asks Iskander if you can share your screen, because if I understand, we have to share our screen by ourselves.
Yeah, I'll just share my screen. Is it visible?
No, it's coming. Okay.
Yes, but not in full screen yet.
Okay. Let's see. All right, I think this should do it. Is it visible now?
Yes.
Yes.
Yeah. Okay. Good morning, everyone. So, my episode, yeah, I introduced myself, Sylvain Massenossi, professor at University of Europe, and with this Kanda, we do our presentation. And this first presentation, we will discuss particularly functional models, how these functional models can optimize network planning and control in the context of next generation network and particularly 6G networks. So I will take the floor for the first 2 points in motivations and some definitions of NDT and functional models, and after I will give the floor for Iskandar to talk about functional models and specific usage in the 6G Twin project. Next, Iskandar. So the motivations, as Sebastian says just before, comes from the fact that modern networks are becoming extremely dynamic. Compared to previous network, 4G, 5G, etc. Traffic is not predictable. We have heterogeneous, this network are heterogeneous. We have different kind of user equipments, connected automotive vehicles, a lot of Internet of Things, drones, satellite. We are talking also about 3D networks. And these networks are more complex also because they are more and more service driven. So we are moving to environment where Internet of Things, edge computing, and autonomous systems continually interact. So in this context, the traditional planning and control approaches are no longer sufficient. So these approaches that are based on static planning or management that are designed before deployment are not applicable. They are usually rule-based. Usually, we use some thresholds that are predefined at the beginning before the deployment, and sometimes we have some manual optimization. So we have human in the loop. And these mechanisms are also not predictive because they are usually reactive to some KPI rather than anticipating them. So this motivates the need to have some intelligence and autonomous mechanism capable of adapting to the network in real time. And the concept appear of network digital twin. Next. So I think it was already defined by Sebastian. So a network digital twin is specialization of what we know already about digital twin with a focus on communication networks. So go to the next, please, because it was already done by Sebastian. I think this architecture will also be defined by the other speakers, but I will go briefly on that because this is the architecture of 6G Twin. This architecture is structured on four main layers. At the bottom layer, we have the physical layer, which includes the real infrastructure, like user equipments, the radio access network, the transport resources, and the core network. On the top, we can see the application and service layer. Between them, we have the network digital twin layer, which is the intelligent core of the architecture. This layer hosts particularly two models, the functional models and basic models we will talk about in the next slide. In addition to architecture, we have the management and orchestration layer, manual layer, that is, as its name indicates, responsible for the orchestration and automation and closed loop control, typically aligned with ZSM. It means zero touch service management principles. Next. So, what is a functional model? Functional models represent, as said before, the intelligent element of the digital twin. We have, as indicated just before, we have basic model and functional models. Basic model describe what is the network is, and functional models describe finally what is the network does. So they are used to predict network behavior, optimize the performance, and support decision making. Ultimately, they enable control actions. They can apply it back to the real network. So functional models, I would say, are the bridge between the data and the decision in future 6G networks. Next. So we have different functional models. depending on the problem to solve. So we identify five main categories. The analytical models that rely on mathematical formulation or modeling and are useful especially for well-defined systems. These analytical models are also used in previous network, 5G and 4G, and other mobile networks. We have AI-based models that are used in 6G twin that are capable to learn patterns from data and particularly effective in complex when the system becomes complex and dynamic environment like 6G networks. We have also probabilistic models that capture the uncertainty in network behavior. And finally, we have deterministic models that follows fixed rules and provide predictable outputs. And we have also, for sure, hybrid models that combine the multiple approaches to balance accuracy and flexibility. Next. Uh, Functional models can be used either for network planning and for network control. For network planning, they are used before, especially before and during deployments to optimize the decisions, what kind of decision, coverage, capacity, and resource allocation. For example, they can help to determine where to deploy the network, the base station, etc., network infrastructure, or how to dimension the resources, the network resources on expected traffic demand. The goals of this functional model for network planning is properly designed before and also during operation. In the other hand, we have functional models that can be used for the control. Uh, they are essential for network control, so they operate in real time compared to the functional model that could be used for planning. They support, for example, dynamic routing. We will have a presentation of this kind of just after traffic steering, network slicing, and control and resource allocations. Uh, they can also no previous slide in Scala. Yeah, they can also be used to enable healing mechanisms where the network automatically reacts to failures and congestion. Next. Functional models follow a structure life cycle. I think that is kind of will go in detail under the other speakers. They are first created, trained using data that we collect from the network, or parameterized and finally either simulated or deployed directly onto the network. When we talk about AI-driven systems, this is the process becomes it's not one-time process, but it operates in closed feedback loop, meaning that model continuously so created, trained, optimized, etc., etc. So the entire process is embedded in ZSM, as said before, the auto service management framework. The key idea of the functional models. So as I said before, it's not static. It means that they remain continuously updated in such a dynamic network like SIG networks, which can ensure that they stay accurate, adaptive, and useful for decision making in these highly dynamic networks. Next. And now I will give the floor to Iskandar to talk about the specific functional models and also life before the life cycle of these functional models and example of functional models we developed in the 6G Twin project. Iskandar, so the floor is yours.
Hello, everyone. Thank you all for your presentations. I am Iskandar Zelagi, a PhD student at University Bourgogne, Europe, and I'm going to be continuing with this presentation. So, as you have seen, CD has just talked about the NDT as well as the functional models, and then the question is raised, where do these functional models fit exactly with the 6G digital twin? Simply put, they live in the digital network domain or the digital domain where they are initiated, trained, and also deployed as NDT instances, which we can see later on in more details, of course. One thing they use is that they consume data from the physical domain, either from the RAN, transport, or core layers, etc., to be fed live telemetry, and they execute either on the edge or cloud, depending on the computational complexity as well as the latency requirements of the functional model itself. One thing that is needed to have all of this system is the NDT Mano or the ZSM that takes care of enforcing the decisions back on the physical network through this layer, of course, after they have been trained and tested on the digital domain, and all of this is done via a ZSM closed loop. So let's talk a bit about the types of functional models we have, and then we'll see an example of how that works really. The first type of functional models that were used, or the thing that was the scenario that was taken care of in this project, is the teleoperated driving, where we talk about the real-time route optimization balancing multiple objectives such as distance and quality of service simultaneously, making proactive handover decisions to keep vehicles connected across RAN transitions, as well as making coverage predictions, anticipating signal degradation before it affects the driver. This would allow us to have a safer, more reliable teleoperated driving experience over our live 6G network. The second scenario that we took care of and its functional models is the energy efficiency in dense deployment. This takes care of the intelligent beamforming and RIS placement which helps us reduce the energy waste at the radio level, the dynamic RAT selection to choose the right access technology per context, as well as the computing energy estimation in order to enable a greener edge/cloud orchestration. This, of course, would allow a significant energy savings without sacrificing network performance. Let's take an example of a functional model that has been created, for example. As we all know, the traditional routing algorithms just pick the shortest path, but our functional model here picks the best one or the right one. We tried to, or we did simultaneously optimize distance, latency, and bandwidth, but via training and a reinforcement learning agent that learns from thousands of simulated scenarios in the digital twin before even making any modifications to the real network. This would allow us to have the best approach that consistently respects latency and bandwidth KPIs without sacrificing route efficiency. Taking into example this functional model itself, how does it really live in the NDT, and how does all of this come together? We can see here that our functional model, excuse me, our functional model is trained in the yellow box in the digital network, for example, and then this functional model itself will be stored in the blue box as an NDT instance. This model, after it has been trained, it can execute in a simulated environment to have the results or the path that is needed that we will take in order to arrive into our destination. And then the NDT Mano will take care of managing the life cycle between the training and execution. And what we mean here is the execution on the digital network as well as the physical network, where we have our results that can be executed on a real environment to arrive to our destination with the respected KPIs. Well, building on this 6G twin architecture, we don't have only one functional model, but the whole team has developed a cohesive system of 14 functional models spanning across both scenarios, which are teleoperated driving and energy efficiency in dense deployment. So the following walkthrough will present all of this system as it stands today. Just a minute, I will share my other screen Is it visible right now?
Yes.
Yes.
Perfect. So we can see here the same 6G twin architecture with the digital domain with its three components, as it has been described as color boxes for the initiation of the and the storage of the functional models, the training pipeline, as well as the execution in a simulated environment. All of these functional models that we have here and we will talk about are stored in the blue box, of course. We have the NDT manual here that we will organize all of this, and of course the physical 6G network where everything will happen. Starting off with our first functional model that has been described just now is the multi-objective route optimizer. As we have explained, it simultaneously optimizes travel distance, latency, as well as bandwidth for the teleoperated driving use case. Here we have it always finds a path that tries to respect the most of the KPIs that we have here, which are a latency less than 30 milliseconds and a bandwidth superior to 20 megabits per second for a safe teleoperated driving experience. The second example we have, also in the teleoperated driving use case, is the handover optimizer using an LSTM and DQN, where it integrates an LSTM-based RSRP predictor with a DQN reinforcement learning for proactive handover decisions that minimizes ping-pong effects and RLFs, or radio link failures, in dense vehicular deployments. Here we can see just below that we have a handover success of 98%. It reduces ping pongs by 40% and radio link failures by 25%. We also have another functional model that also took care of the vehicle routing. But this one actually computes the road segment sequence that minimizes total route length between start and target by selecting the optimal next segment at each intersection via DRL. The thing is that this functional model, for example, uses another functional model with it, which is a coverage predictor that estimates SINR values at every map coordinate using a random forest regressor trained on vehicle trajectory samples. This allows it to produce a coverage heat map for connectivity-aware routing that the third functional model we presented can use. Going on a bit on the second scenario, which is energy efficiency in dense deployments, we have our functional model that takes care of position-guided multi-armed bandit with UCB exploration for millimeter wave beamforming codebook selection that leverages UA locations to reduce search space in RIS-assisted deployments. This has an energy efficiency of more than 30%, and it reduces computation time by more than 30% as well. Another one we have is the RIS placement optimizer, which determines optimal RIS placement coordinates in indoor environments using polyhedron optimization with Siona ray tracing to evaluate coverage and blind spot elimination, which also have an increased coverage by 10% and an energy efficiency of more than 30%. We also have a network energy consumption estimator that estimates the total network energy consumption given cell traffic load, beamforming vectors, and hardware parameters that is validated against the VIAVI RSG emulator, which also has an estimation accuracy of more than 90%. Next up, we have the RAT selection and cell shutdown that assigns UEs to available RATs and shuts down the underutilized cells to reduce energy consumption while maintaining service quality. This also has an energy saving of more than 30%. Next up, we have two functional models that will be later jointly used for another one. The first one being the MEC E2E latency estimator that estimates application E2E latency under varying run load and Kubernetes resource allocation at the MAC layer. that uses RAN topology and compute utilization as inputs. This one has an a resource utilization of more than 30%, and the compute energy has the energy saving of more than 30% that estimates energy consumed by Kubernetes deployment based on active replicas and resource utilization, enabling energy-aware scheduling at the MEC node. As I've said, these two are actually jointly used in order to have a single model for Pareto optimal resource allocation with both KPIs that were presented. Going back a bit onto the teleoperated driving use case, we have another functional model. As you can see in all of the examples, we can always see which parts of the physical 6G network it needs to interact with in order to make the decision, in order to optimize the network. Here, for example, we have a multi-agent proximal policy optimization-based cooperative multi-agent reinforcement learning for dynamic multi-UAV aerial base station deployments that uses a centralized training and decentralized execution architecture in order to maximize coverage and spatial fairness simultaneously. This one has a bit of different KPIs with a mean coverage of more than 87%, a Jane fairness index of 1, and an inference less than 1 millisecond per step. Last but not least, we have also two other coverage predictors. The first one using a Gaussian process regression trained on sparse measurement collected at random indoor locations in the LIST 5G lab network that produces RSRP heat map supporting teleoperated driving with an indoor accuracy of more than 95% and a computational cost of O to the n cube. The second one is an also coverage predictor, but it actually uses a convolutional neural network trained instance specifically on sparse RSRP movement. This one also performs learned spatial inpainting. Non-RSRP samples serve as both as inputs and supervision signal in this case to reconstruct unmeasured locations as an RSRP heat map. Of course, with an indoor accuracy also with more than 95% and a computational cost of E to G. This has been all the functional models that have been created thus far by all of the partners in the project, and I leave the floor to who's coming next up.
I hope now it's clear how functional models can provide a key enabler to optimize network planning and control by combining AI, data, closed loop planning as the same framework, and the idea of if I don't know if it's up to me to introduce the next speaker. The idea is to move to the federated simulation platform that we present in the architecture, which is in the orange color. I give the floor to the second one.
Hello. Am I audible?
Hello, Pritam. Yeah, we can hear you.
Okay. Is my screen visible to you?
Yes.
Okay. So, hello everyone. My name is Pritam. I'm a PhD student at TU Dresden at the chair of network system modeling. And today I'm going to talk about federated simulation platform that has been developed by our chair in the 6G Twin project. So in this presentation, I'm going to talk about that, introduce you with the framework, talk about how does it work, how does it couple simulators, and then how it is being used in a use case simulation in the context of 6G Twin. So to introduce the framework, that what does it do and why it is needed, basically this diagram over here on the right explains the high-level job of the simulation framework. Now we can see that there is a middleware platform and generic interface, which is generic enough to apply semi-specific rules in order to couple heterogeneous simulators. So we can see different network simulators and mobility simulators are being connected with the middleware as an plug and play fashion, and making an interconnected system. So this is a well-known question, that like, why to couple simulators? Because it lets the researcher to analyze a complex interconnected system and cover broader area. So a simulation framework such like this will allow you to perform what if scenario analysis. And in the context of 6G twin, this framework will be used for the teleoperated driving scenario. Now, to show that architecture, I'm pretty sure that my colleagues before me has already presented this architecture. This is the architecture of the 6G twin, and this is exactly where in the orange box, where the simulation framework falls. And the two main important blocks in this, I'm not going to talk about all the blocks in the architecture, but to remain within the scope of this presentation, I'm going to talk mainly about the yellow box over here, and more specifically about the orange box, which is covered through this simulation framework. Now, if we see this diagram, and this is a bit complex diagram in my opinion. To simplify this, I have added a simplified version of the framework, where it represents the workflow of the architecture. And we can see a simplified version of the same architecture, and we can see that in the yellow box there is this AI training and optimization block is present over here, and this block is actually communicating with the simulation framework, with our simulation framework, which is in orange, through an NDT instance. So a simulation framework can perform what-if analysis. Therefore, in order to train and optimize an AI model, the AI model can control the simulation run of the through the simulation framework, change the parameter of the simulation, and keep running and keep collecting results and get trained. After training, it can it can make decision on the real physical network through NDT Mano. So now we understand that the simulation framework not only integrate simulators, but it also provides a mechanism to be controlled or to be launched by the NDT instance. So now, how does the architecture of the simulation framework looks like? So you can see that I have represented all the important blocks, important modular blocks of the framework, and there are more detailed reasons that why each block is added, and how it helps to make the architecture more modular. But I'm going to talk briefly about it. First of all, like as we have seen in the 6G twin architecture, that the simulation framework job is not only to perform interconnected simulation, but also allow an option to be controlled remotely, and therefore it exposes a server which is called CoSIM server, which is directly being connected with the NDT instance, and this NDT instance can control the simulation framework through this server. So what it can do, it can use the CoSIM server to modify the configuration file of the overall simulation, and then make the simulation framework start a simulation using the connected simulators, which you can see on my right, where different simulators, network, UAV, traffic simulators are connected and perform a simulation. At the end of the simulation, it is the job of the framework to collect the result and then forward it back to the NDT instance, where NDT instance can further forward it to the AI optimizer, where it get trained, and then it might decide to run and rerun and keep changing the configuration using only one instance of the co-simulation framework. And these two blocks you see, this is the master scenario manager, which is the main orchestrator of our simulation framework. And in order to separate the simulator-specific interactions, we also provided a dedicated scenario manager, which basically handles the simulator-specific interactions. For example, calling a specific service over an IP, handle authentication, and so on, right? And also the red lines that you see, these are the communication. So our inter-process communication, it can be distributed, remote distributed as well. And we have used gRPC along with protobuf in order to make this communication possible. And to since controlling a simulator requires some service or a server implementation, therefore we provide a protocol translator, which is simulator-specific implementation of the RPC services that are defined in the using the protobuf file. So this block also helps to compartmentalize the simulator-specific interactions, such that if I say that some project member might have some proprietary simulators, and maybe due to some rules and regulation, they are not allowed to share their interface specifications and so on. Therefore, having a protocol translator will help them to hide their or make the interface specifications, keep their interface specifications private. And also, these are not the only simulators that can be coupled with the framework. These are just examples, but the main advantage is that it can work as plug and play, and such that any simulator can be switched between another similar simulators and so on. Now, we have seen the architecture. Now I'm going to show one example that how does it look like through a video demo. So this is the configuration file, and there are several simulators that are connected, and this active means it is turned on. So at this moment, I can see Sumo and Omnet. These are the only two simulators that are active in this simulation environment. And if I run the middleware, I can see that, okay, this is on the left-hand side, I see the GUI of Omnet, and on the right-hand side, I see the GUI of Sumo, where the Sumo's job is to simulate the movement of vehicles, and Omnet's job is to perform this wireless communication, which is being represented through a blue dot, which is moving very fast. And we can see that like the vehicles information is being flown from the Sumo through the middleware, and then being transferred to Omnet for network simulation. Now, this is done. Now, if I go back and then I activate one more simulator, which is called AirMobiSim, which simulates the mobility of UAV, and I can, if it starts, then since AirMobiSim doesn't have a built-in GUI, therefore no GUI will appear for AirMobiSim, but we see the same GUI for Omnet and Sumo once again. But this time, since we activated AirMobiSim, then we see that there is, along with the vehicles that are being simulated, the UAVs are also taking part in the simulation and communicating with the vehicles and making it possible that to perform this interconnected simulation, that what if on top of a intersection, if there is a UAV, can it help for in the communication and so on. So there are two UAVs that are being simulated, that is being represented, and the vehicles that with the same position is being transferred to Omnet, as you can see on the right and left using the same map. Okay, so that was the demo of the simulators, and you have seen that how it can be switched on, switched off through one change in the configuration files. So at present, we have coupled 5 simulators with our simulation framework. We have coupled Omnet along with Simu 5G library for 5G communication. We have coupled Sumo for traffic simulation or the mobility simulation of vehicles. We have coupled AirMobiSim to simulate UAVs in the simulation. We have also coupled Spacefence for the simulation of LEO satellites. And we have also coupled a custom application simulator to simulate the application logic for the simulation. Usually, the application logic is simulated through a network simulator, but since this is a loosely coupled framework and the framework should not be dependent on any specific simulator, that's why we have also coupled an application simulator to make it independent of any simulation component. Now we have seen that how the architecture looks like. Now, if I briefly show you one very important concept in coupling simulator, that how does it interact with all the simulators to perform this synchronization. Now, this on the left hand side, this is the middleware that is being represented, and let's say there are 3 connected simulators, A, B, and C. So this has been divided into 2 parts. The first block over here happens at the initialization phase, and the second block happens iteratively throughout the simulation. So even before the simulation loop starts, it performs some initial queries. So the middleware keeps polling all the simulators. Hey, do you have any request, or do you want any data from another simulator, and so on, right? So why it is needed? Because as you have seen, so we had a network simulator, Omnet, and it is taking the input from Sumo. For example, they are using the same road network, same building structure, and so on. So these are the information that had to be taken out from one simulator and had to transfer in other simulator, which is not playing an important role in simulation, but in the visualization and so on, right? So this kind of information might be required. So that's why the middleware ask different or poll different simulators to submit any request of data. And then whenever it is requested, the middleware gets get those information from the required simulator and then forward it back to the simulator who asked the information. Now, in an iterative process, what does the middleware do is that, like at the synchronization phase, it asks or poll all the ask all the or command all the simulators to move to a certain step or the synchronization step. So once all the simulators advances to a common simulation time, then the middleware ask or poll all the connected simulators to submit any interactions, any vehicle information status update they want to exchange or get or set any information to another simulator. And it polls for the information, and upon receiving it, it just goes to a specific simulator or the requested simulator and perform this action. Now, we have seen the architecture and also how it interacts. Now, if I talk about that, how does it, how can I use this simulation framework to couple one more simulator with the simulation framework, right? So this simulation framework can not only integrate simulators, but it can also integrate functional model as described by my colleagues before me. For example, an AI model and route optimizer model and so on. And in order to do it, what it needs to do is that, like, it needs to implement some of the services. There are 7 services defined in protobuf language. This need to be implemented. After these services are implemented, then a dedicated scenario manager should be created within the simulation framework, as I have shown in the architecture diagram, to manage this simulator-specific interaction. And then the entry for the new coupled simulator had to be entered in the configuration file. So the configuration file has to be updated to make the middleware know that, okay, there is a new registration, new federate, which is taking part in the simulation. Now, we know all the important things about the simulation framework, and the question is, how is it going to play a role in the context of 6G Twin project? So in the 6G Twin project, it will be used for simulating teleoperated driving use case. And more specifically, it will simulate a specific area in Luxembourg. Let's say in a geographic location, there are certain base stations and user equipment that are present, and a vehicle wants to travel from point A to point B. Now, while traveling from point A to point B and being controlled by a remote operator, it might go through certain areas where the network connectivity is not so good, or a base station is missing in order to provide provides a good connectivity. Now, in scenarios like this, the main objective is to transfer from the terrestrial network coverage or address the network gap. It will shift the network connectivity from through base station to through satellites. Therefore, in the perspective of simulation framework, the network simulator, which was providing the network connectivity through base stations, will now shift its connectivity from the terrestrial-based network simulator to the LEO satellite network simulator and make this simulation possible and maintain seamless communication throughout the journey of the teleoperated driving. And last but not the least, this is the location where our framework has been published. Sorry. So we are also working to put it in version called platform called GitHub. It will be added soon, and also the information should be updated in the same link. We have also presented a QR code. If you scan this, it will directly take you to the site where the software has been released. Thank you for your attention.
Thank you very much, Pritam. And I think our next speaker will be Luis from Ubiware.
Yes, can you hear me?
Yes, we can hear you.
And can you see my presentation?
It will come in 1 second. It's online now. We can see it.
Perfect. So, good morning, everyone. I'm Luis Santos from Ubiware, a part of the research team. And today I will present our current proposal for a web-based co-simulator framework in the context of the 6G project. We've seen in the previous presentations how we take the functional models and the simulation framework together in the 6G NDT architecture. Now I will present the design rationale behind the interface between both of these and how we can support the different demonstrator scenarios that were defined in the project. The main idea is simple. So 6G has several heterogeneous use case scenarios with different simulators, data sources, KPIs, and methodologies. Because of this, we need a common web-based layer that helps users access, configure, monitor, and interpret these scenarios in a coherent way. So why a web-based interface? The motivation comes directly from the structure of the 6G demonstrators, as I mentioned. We have two major use cases in the project. The first is teleoperated driving, where the focus is on service continuity, low latency, reliability, and mobility support. And the second one is energy efficient network management, where the focus is on reducing energy consumption while preserving quality of service and service level agreement requirements. Both of these use cases are further divided into several scenarios, and each of these scenarios have their own technical environment. Some rely on physical test beds, others will most likely rely on simulation or emulation scenarios. Some of the focus can be placed on radio conditions and handover, others on beamforming or edge computing orchestration. This means that we do not have a single homogeneous demonstrator. So we have a portfolio of scenarios, each with different data sources, simulators, KPIs, and validation methods. So this is why a web-based interface is useful. We have to provide a common access point for the different 6G scenarios, and we do not want to hide the difference between the scenarios. We want to make these differences more explainable and more comparable, as well as easier to navigate by the users of this dashboard. So the problem that we have identified is that the traditional approach of a monolithic dashboard that would centralize everything would not work well. If we try to represent every scenario using the same charts and the same metrics, we would lose a lot of technical depth. The scenarios are chosen to be different to represent different scenarios, obviously. So this would be a pain point for us in the monolithic setting. For instance, in the teleoperated driving scenario, the most relevant information may be handover timing or video bitrate. But in a millimeter wave and risk optimization scenario, the information that is relevant is completely different. So it could be risk configuration, SINR, among others. So the challenge is to balance these requirements. On the one hand, we need project level coherence. So stakeholders and users should not feel like they're looking at 5 unrelated systems. Um, our interface should have a common navigation platform, consistent with consistent visual logic and comparable validation outputs. On the other hand, we need scenario-specific fidelity. So each scenario must be allowed to show the metrics and technical details that actually matter for its own validation. This is why our proposed approach is a federated dashboard. So the dashboard provides a common structure, but lets each scenario keep its own technical view. A key message for our dashboards that it does not make the project output look simpler. It makes the complexity understandable. This first part of our federated web dashboard concept, um, we we propose one entry point into multiple scenario-specific technical views. The idea would be to have a consistent validation methodology while letting each scenario expose its own inputs, outputs, and KPIs. At the top level, each user would interact with the web interface and select a scenario they want to analyze. From there, the interface would provide access to scenario-specific dashboards. For each scenario, the same general logic can be followed. First, the interface allows relevant inputs, so telemetry, simulation parameters, model outputs, or configurations. Then it shows the NDT related logic, so predictions, what if analysis, optimization, and decision outputs. Finally, it shows the KPI results, ideally comparing baseline operations with NDT assisted operations. Um, the baseline versus NDT assisted comparison, is very important. Across all of these demonstrators, we want to show that the value of NDT is not saying that the NDT exists. It must be shown that by comparing the baseline with the NDT assistance, we can improve the normal operations of what all of these scenarios are. So the role of this dashboard is not just visualization, it is also validation and explainability of the NDT predictions, the NDT decisions, and how this all affects the final performance indicators. The second part of the link between this dashboard and the 62 in architecture, we want the dashboard in our architecture belongs in the application layer. It is what we say as the human-facing interface between the NDT ecosystem and the stakeholders. A full network digital twin architecture may include several domains, different functional models, different data repositories, and simulation tools. Uh, but in practice, for a given scenario, we instantiate a specific NDT instance. So this instance contains a specific subset of data, models, and simulation capabilities for a particular task. The dashboard will then expose the NDT instance for the selected scenario, and along with it, the scenario dashboard, which will allow for the visualization, possible control, and connection to the underlying data models and the simulation framework. From the user perspective, the expected flow is quite straightforward. The user selects the scenario, the system reconstructs the telemetry state or the simulation state according to the specific scenario. The NDT performs the analysis or the what if evaluation, and the dashboard would present the KPI outputs comparing the baseline with the NDT assisted operations. Um, sorry, after defining the motivation and how we plan to set up the federated web dashboard, um, we can look at how this applies to the actual 6G twin use cases. The 5 scenario dashboards follow the same general structure, but each of them has a specific technical focus. For use case 1, the focus is on teleoperator driving, with scenario 1 being a more controlled setup based on NDT assisted operations and a high priority autonomous system, while scenario 2 of use case 1 expands this into a larger network simulation that focuses on route optimization, predictive handover, as well as potential terrestrial and non-terrestrial connectivity. For the use case 2, the focus is on energy savings. So scenario 1 looks at millimeter wave and risk optimization. Scenario 2 focuses on multi-band network management, as well as base station activation, sleep, and different modes. Uh, and scenario 3 extends this problem across different domains. So linking RAN with edge and cloud computing orchestration. For each scenario, the dashboard should help to answer the same core questions. So what are the inputs? What does the NDT and the simulator do with them? And what are the KPI outputs that demonstrate the improvements? The first use case scenario focuses on NDT assisted operation for a high priority autonomous system. This is represented by a teleoperated robot dog. The technical problem is mobility under strict service constraints. The robot dog sends uplink video and telemetry to a remote operator while receiving downlink control commands. This means that the network must maintain low latency, high reliability, and sufficient throughput, as well as stable radio conditions. A key event in this scenario is handover. The network responds when radio conditions indicate that a handover is needed, but for teleoperation, waiting until this last moment to perform this handover can be risky. And can also cause latency spikes, packet loss, or video degradation. So our NDT assisted approach is to be proactive in this handover process. So the system monitors radio conditions, cell load, and service level metrics, and it aims to predict that the robot dog is approaching a specific handover region, and then triggers these actions before the handover happens. Um, these actions can be something like the target cell preparation, load relief, or traffic steering. For the dashboard itself, the most important point is cause and effect. We want to show radio conditions, the predicted handover, and also the NDT action, as well as the actual handover events and the impact on the quality of service. So some useful visual elements could be the SRP or the SINR timeline, serving cell timeline, or specific metrics regarding video bitrate or packet loss, as well as the output by the NDT triggered actions. On use case 1, scenario 2, we have this large network simulations I have mentioned. So we scale the problem from a controlled testbed to a larger and more heterogeneous simulated environment. The focus here is network-aware teleoperation across a realistic urban area. The scenario includes vehicles, it includes UAV, as I mentioned, NTN, moving through the environment, while the network conditions vary along the route. It may also include satellite links as well. And the approach, the baseline approach, would be more reactive to the route selection. So route selection could be made based on distance, based on mobility constraints, and the handovers occur when the current connection degrades. But as in the previous scenario, we don't want this for teleoperation. We want to use the NDT assisted approach to predict and proactively make this decision. So the NDT evaluates network conditions along the routes, predicts different coverage gaps or congestion, and supports route adaptation, predictive handover, and multi-link management. For the dashboard itself, the most intuitive visual is a map. So the user should be able to compare baseline routes with optimized routes and also understand why the optimized route could be better for teleoperation. So slightly different routes that might not be the shortest one could provide better latency or better reliability. The dashboard should also show some important metrics like delay, jitter, packet loss that are relevant to the use case scenario. And these metrics will help connect all of the mobility decisions of the NDT with current network performance, combining route planning and network planning together. So for use case 2, scenario 1, this first energy saving scenario focuses on radio level optimization, specifically millimeter wave and RIS or reconfigurable intelligence surfaces. The technical challenge is that millimeter wave bands offer very high bandwidth, but they are also quite sensitive to blockage or path loss. To maintain a good link, we need effective beamforming, and traditional beam sweeping can introduce quite a bit of overhead, which is not quite efficient when we're trying to save energy or when the user position is quite uncertain. RIS or reconfigurable intelligence surfaces can help by reflecting the signal towards the user when direct paths are blocked. But RIS itself must also be configured correctly, so the system needs to select appropriate beam and appropriate RIS configurations so that they improve link quality without wasting power or computation resources. In this scenario, NDT supports the evaluation of DT-assisted beamforming and RIS configuration. So the dashboard should help show how predicted beam choices, RIS configurations, and link changes affect important metrics like SNR, data rate, transmission power. And alongside this, the dashboard should also show selected beam versus optimal beam, SNR, or data rate time series, and obviously how the baseline versus the NDT assisted beam selection decision helps configure the risk decisions and show that we can improve both performance and also energy efficiency. For scenario 2, we have a energy saving scenario that's focused on radio link optimization and also network level energy management. Here, the network combines sub 6 gigahertz covered cells and millimeter wave capacity cells. So these coverage cells provide broader service availability while millimeter wave cells provide high capacity. The challenge is handling user demand changes over time. So at some moments, high capacity cells may be necessary. At other moments, keeping them active may waste energy across the network. So the role of the NDT is to support the scenario by performing a what-if analysis over different network configurations. It evaluates which users should be assigned to which base stations or frequency bands, and which beams should be used or base stations to be placed into sleep mode or deactivated in order to save energy. The most important trade-off to show to the user is energy saving versus quality of service preservation. It is not enough to show that we reduced power consumption. We must also show that we kept with the required data rates metrics, and also which SLA violations are avoided. So some useful dashboard elements could include base station status, like active, sleep, or shutdown, specific total or per base station power consumption, SLA satisfaction or quality of service score, and also the baseline versus the DT optimized configuration. And for the final use case, we focus on cross-domain interactions, specifically between the RAN domain and the computing domain. This is important because energy-saving actions in the RAN can affect the traffic that reaches the edge or the MAC platform. If specific base stations are activated or deactivated or placed into sleep mode, the computing domain may see some changes in the workload patterns. In a baseline situation, the computing platform reacts only after changes occur. For this, it may have a very high overhead of resources just to be safe, or it may scale too late and risk quality of service degradation. With this NDT-based federation, the computing domain can anticipate information from the RAN NDT. This allows for the computing side to anticipate traffic variations and select better scaling policies. The goal is to reduce computing resource usage and energy consumption while maintaining service reliability and latency requirements. For the dashboard itself, the key is cross-domain causality. So we want to show how the RAN side affects the computing side. For example, a change in connected users or traffic volume leading to increased MAC load, triggering scaling decisions that then affect values of latency and energy consumption across the network users. This dashboard should include different RAN metrics like traffic and connected users, and from the computing side, CPU and memory utilization, Kubernetes metrics, like node and cluster energy consumption, and also trade-off point of view between the baseline and the NDT assisted latency versus energy trade-off decision making. So to finalize, this is the current progress of our work. The first step to select the prototype scenario, which is already done. The next step is to define the minimum dashboard data schema, which are already identified. This is important because implementing a full interface, we need to know specifically which inputs, outputs, and events, as well as the KPIs that are tested in each scenario must be exposed. The next stage is connecting the available telemetry, the Grafana panels, and the API outputs of the different scenario testbeds. After that, the priority should be implementing a common dashboard shell with a scenario selection and a consistent layout between scenarios. And once this common shell exists, we can add the scenario-specific models. These should support baseline versus NDT assisted comparison because this is the core validation logic across all of these demonstrators. After that, the interface can evolve toward what if configuration. So simulation result views, alignment with the NDT descriptors, and also mono life cycle mechanisms. And finally, KPI reporting for validation. The maturity level on this side will summarize the evolution we expect for our dashboard. So just level 1 is visualization. Level 2 is scenario selection. Level 3 is what if comparison. Level 4 simulation control, and level 5 would be the targets, so NDT assisted decision support. The important point to highlight here is that we do not need to reach level 5 immediately. So a useful first prototype can focus from just level 1 to level 3, making that the demonstrator outputs visible, understandable, and comparable. And the final goal for our web-based Go simulator dashboard is that we want to connect the NDT architecture, the simulator framework, and the demonstrator validation process in order to provide an explanation layer for how our NDT assisted decisions translate into measurable inputs. Thank you to all the listeners.
Thank you, Luis. So we have a few minutes left. Before we conclude, I would like to open the floor to any questions the audience might have. So please feel free to write them on the chat. At the moment, I don't think we have any questions. So as there don't seem to be any questions, I would like to thank all the speakers for the presentations and all the participants for joining us today. This session was a valuable opportunity to share the progress of the project so far and discuss the work being developed. The recording of the webinar will be available soon, so please follow us on social media to stay updated. And you can also get in touch with us if you have any further questions. And thank you once again, and have a great day.
Thank you, everyone.
Thank you, everyone.
Bye. Bye-bye.
Bye-bye, everyone.